Chemicals! Hello, my sweetnesses. So to pick up where we left off when we were talking about chemicals in class, the focus of this is going to be how do we actually quantify how toxic a chemical is. So in the past, we just look at evidence of like what would happen when humans would be exposed to this. However, we can't do testing on humans. It's kind of unethical. So what we do is we do these things called LD50 or LC50 studies, and these are done on animals. So we're going to get more into the details about what are these studies. So what is an LD or LC50 study? LD50 stands for lethal dose, and LC stands for lethal concentration. They're both 50, so that relates to the fact that either of these tests are testing the dosage or concentration to kill half of a test population. So we said, like we had on the previous one, I had a picture of like rats. In an LD50 study, what we're going to do is feed a whole bunch of rats, of different groups of rats, different amounts of chemical, and determine the amount that kills the half of the test group. For concentration, this is doing the same thing, except we're dealing with materials that you basically are surrounded by. So if you're a fish, you're not necessarily eating the chemical, but you're immersed around the chemical. So the LC50 is used a lot for aquatic materials, and the LD50 is used for ingested materials. What does these studies or data actually provide? Acute toxicity. So what amount of it will actually cause basically immediate health problems or death. So how do we actually compute LD50 from an experiment? So basically what they're going to do in an experiment is they're going to set up multiple groups of rats or fish. In this case it's fish. So we've got 6 groups of fish. This group is going to have a control amount of dilution of toxin, which basically means it's going to have no toxin in it. And this group is going to have no dilution, which is going to be like full, all toxin. All right, full, not full, full amounts of toxin. And then we're going to give like a little bit of toxin here, and then a little bit more, and then lots here. And basically it's going up in this way. We put the same number of creatures in each bin. The only thing we're changing is the amount of toxin in the group, and then we watch and determine how many of them die. So we put all these different animals into different groups. Some of the groups get exposed to no toxin, some get exposed to lots of toxin, and then eventually what the heck do we graph? So we're going to graph on the x-axis the dose. And so over here we have the lowest doses, and over here we have the highest doses of chemicals that you administered to different groups of organisms. And then what we graph then is for each different level of dose is we graph the response, which in this case is how many of them died, or mortality. So here you have 0% mortality and 100% mortality. So you graph for each different concentration or dose a different level of mortality, and then you get this lovely kind of dose response curve, which is usually this S shape. And that is what we end up using to calculate the actual LD50 or LC50 value. We also use this curve to determine something called the threshold value. The threshold value is the point at which we start to see an increase in baseline mortality. So here is the point at which all of a sudden mortality starts increasing from its basic baseline values. So this is the threshold point or toxicity. So let's let the magic begin. Here's our example, so you're just going to watch and follow along if you want. I know what you've been asking for this whole time. You're like, what we really want to do, Samler, is kill a bunch of brine shrimp in CuSO4. Well, good news, here is the data for you. CuSO4 is copper sulfate. So here's an experiment, and basically in this experiment, they have set up 1, 2, 3, 4, 5, 6, 7 groups. Each of these groups have a different concentration. This column expresses the concentration of the pollutant in percent, and this column presents it in milligrams per liter. They're both expressing the concentration, how much of the solution is filled with toxin. So here we've got 0.00001%, and here all the way down here is 10% concentration. So we have low to high concentration from the top down. And then all you do is you set up these 7 dishes, each with their own separate concentration, and you watch. And it says after 48 hours, we measured how many died, and here's the information that died. How many shrimp were in each dish? 200. So 20 out of 200 died in this one, 20 out of 200 died in this one, and so on. So that was your problem, so let's show you how to solve it. Step one, first thing I do is you're going to figure out the percent death or percent mortality. So you're going to figure out what you have the number that died, now figure out the percentage. So every group was out of 200, so here 20 died, and there was 200 in the bin, so 20 divided by 200 times 100 is 10%. That means this one here is also going to be 10% because it's 20. This one also is 20, so that's a 10% mortality rate. 40 is 40 divided by 200 times 100, which would equal 20%. 110, you're going to take 110 divided by 200 times 100, that will be 55%. Here is 90%, and here all 200 died, so that means you have 100% mortality. That's your step. Figure that out first. Okay, step two now is to label your axes. So I'm going to label the y-axis first, which is the response. And the response when you're exposed to a toxin is you'll die in these experiments. So we're looking at percent dead. So here we have 0% dead. And you'll notice that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means this is 100% dead up here. That means we're at 50. So each of these lines equals 10%. On the bottom was the dose, all right? And remember, there were two types of doses. We expressed the concentration in percent, and then we also expressed the concentration in milligrams per liter. So the first one that was on the lowest dose, or the lowest concentration that we had on there, the percent was, from the previous slide, was 0.00001, and the same concentration, but in milligrams per liter, was 0.00005. So that's represented right there. Then right here is the next one, so that would be the next one on the list that was higher, so that was 0.0001 or 0.0005. I put both of the types of concentrations down in two lines. Then this one would be 0.001 or 0.005. And all I'm doing is going from the smallest concentration to the largest that was in the table. So that would be that, that would be that. Here, the next highest one were these. Then there was a 1 and a 5, and then there was a 10% concentration and 50 milligrams per liter. So that's what we want to do next, is label your axes. All right, so now that we have the graph labeled properly on both sides, it's time to actually plug in the data from each group as to how many died per dose, and then we'll make a little line, or the actual curve, and then figure out the LC50 in this case, since it's brine shrimp in a solution of copper sulfate. Just to refresh ourselves, the mortality that was computed from the couple tables ago, from a couple slides ago, was the first one had 10%, then 10%, then 10% mortality, then the fourth group had 20%, then 55% for the fifth group, then 90, then 100. So that's just a review. We've already calculated that. So the first, or the lowest concentration, had 10%, so that would be right here. So we're going to go up to the 10% mark and mark that in there, which would be graphed right there. Then the next group also had 10% mortality, so we're going to graph right there. Then the third group had 10% mortality, so we have that. The fourth group had 20%, so that's graphed there. Fifth group had 55%, so that would be graphed right there. And then the sixth group had 90%, and our last group had 100%. They all died. So now that you've got them all graphed out, you just connect the dots to make this little curve, and voila! You've done it. You've made a dose-response curve. I'm so proud of you all. You're so wonderful. So now the question is, what's the dang LC50? So how do you compute this? Is now you're actually going to go to the y-axis, and here is the 50 degree. This is the point at which half of the group is dead. So you're going to follow this all the way until where you hit the curve. So here I hit the curve right here. And then we drop down to figure out what is that amount or that dose. So it's following this line. And voila, that's the amount that is actually the quantified amount that kills 50% of this brine shrimp population. So what is the exact number? Well, we know it's somewhere between 0.01 to 0.1%. And we know that it's somewhere between 0.05 to 0.5 milligrams per liter. But the question is, what exactly? So to figure out the exact amount, start at the first portion here. So here is in that bracket, the beginning of that bracket is for percent is at 0.01. So what that means is that each additional line is now worth an additional 0.01. So this is 0.01, so this is an additional 0.01, so for 0.02, this is 0.03, this is 0.04, this is 0.05, this is 0.06, and so that means that this one right here is 0.07. So the LC50 in a percentage expression is going to be 0.07. To figure it out for milligrams per liter now, the starting value for milligrams per liter at this point is 0.05. So that means each additional line is going to be worth an additional 0.05. So here we're starting with 0.05. Add another 0.05 here to make it 0.1. Then add another 0.05 to make it 0.15, 0.2, 0.25, 0.3, and that means right here is 0.35 exact measurement of LC50 in milligrams per liter. So these are your actual LC50 values for this particular experiment. The other thing you're going to want to be able to identify is the threshold value. Remember, the threshold value is where from the baseline starting background death rate, where does it start to increase? So here we see a consistent death rate all the way through these concentrations, and then we see it go up after that. So that means right here is our threshold value. So to summarize, when we calculate the exact LC50 from the graph, it was a 0.07 concentration or 0.35 milligrams per liter concentration. What does that mean? It means if you made in this experiment a 0.07 concentration of copper sulfate, or that's the same in this experiment as 0.35 milligrams per liter concentration, that 50% of the test population died. The threshold level for these were 0.001 and 0.005, which means that was the point where we started to see increases in the amount of mortality. All right, so it's your turn now. You have 2 sample problems to give you a shot here to see if you can do this. So take a moment, read this sample problem number 1. You've got paper in front of you here to map out your ideas. So try it on your own. The experiment here is calculating the LD50 for caffeine. In this experiment, you feed 7 different groups of rats caffeine, and then each group has 50 rats, and you've counted up the number of dead rats. So the 3 things you need to do is determine the LD50 for caffeine using the graph method, then figure out the threshold using the graph, and then once you have the LD50, see if you can calculate how much caffeine it would take to kill a person if they or estimate that based on their mass of 80 kilograms. So pause here, take a moment, and try this out, and when you're ready, then you can unpause the video and see the solution. Alright, so here's the solution to problem 1. Here's your concentrations. The lowest concentration is here to highest, low, here to high. We have percent and milligrams per kilogram for caffeine. Here's your number of dead rats. Remember, everything was out of 50, so I've already computed what this means to percent. So this is the percent. So you had 4, 4, 10, 28, 42, 62, 100. All right, so check yourself here. Here's for problem 1 for the caffeine one. I've already labeled the axes, so the Y has the percent dead, and I've put the 2 different versions of concentration on the bottom. And all now I'm going to do now is map in the percent mortality. Notice that you always put on the bottom the lowest concentrations first and the highest concentrations last. So in the table, the concentrations were started from high to low, so make sure that you order them properly from low to high, which means you'll have to start at the bottom of the table and go up. So for the lowest concentration in the table was this, and that was a 4% mortality, so that would be right here. And then the next concentration had also a 4% mortality, so that's right there. Then the next one from the table was 10%, so that would be right there. Then the next one was 28, so that's 28 is right there. 42 was next, so 10, 20, 30, 42. Then we had 62, so we have 10, 20, 30, 40, 50, 62. And then 100. So it's a different shape of curve, but it's a curve nonetheless of the toxicity for this particular experiment. And then you are going to determine the LD50. So here is the 50% line. So we're going to draw this line all the way until it hits here. So it hits here. I'm going to just pick the closest one. So I'm going to pick it right here. Pick the closest line that it crosses at, which would be about right here. So it crosses right there. So that means it's in between this section right here. So this is the 1 section. So that means each additional line till I get to 10 is worth 1. So that means I'm going 1 line up. So that's worth 2. And this is also right here the 20 line for milligrams per liter. So then I'm going to add an additional 20 to get to the next line. So that means we're at 40. So I have a 2% concentration LD50 for this, or a 40 milligrams per kilogram. Oh, I'm sorry. Down here I put milligrams per liter, but it's really milligrams per kilogram. Additionally, we should also look at where the threshold is. So the threshold is where do we actually start to see an increase. So we had the same mortality here, and then after that it starts to go up. So this is our threshold amount. That is what we're going to say is our threshold level, 0.001 and 0.02. So in conclusion, we had a 2% LD50, or that also is the same as 40 milligrams per kilograms. So if you feed this particular population, 2% killed half of the group, or 40 milligrams per kilogram. The threshold level where we started to see, after that we started to see an increase in mortality was 0.001% concentration, or 0.02 milligrams per kilogram. Now, how do you take this and use this to actually make an estimation about how does this affect humans? Well, humans, we will figure out the mass, so you can only do it for a particular set of mass of humans. So we're saying that this group of humans is worth 80. So we have an 80 kilogram human, and we want to know how much caffeine would it take to kill half of a group of people with that age class or weight class. So we've got 80 kilograms. We know that from up here, the LD50 was 40 milligrams of caffeine per 1 kilogram of body weight. So you would cross those out, and what you're left with is 80 times 40, which is 3200, and then the unit is milligrams of caffeine. So even though we can't test on humans, we could make an estimate of what would be toxic to humans, which in this case would be, we're estimating from this experiment that 3,200 milligrams of caffeine would kill half of a group of humans at the mass class of 80. All right, here is a second sample problem. This one's involving VX nerve gas. You're doing an LD50. This time there's only 6 groups. Each group had 150 rats, and then you measure the number of dead. So again, figure out what is the LD50 for this experiment for VX nerve gas, what is the threshold limit, and then figure out how much it might take to kill humans with a mass of 90. So take a moment, pause, try it yourself, and check the answers in a little bit. All right, so here again are the concentrations. The concentrations starting from low to high here. We're dealing with percents and milligrams per kilogram. Again, everything was out of 150, so then to get the percent, you divide by 150 and times by 100. So we have 100% dead, 100% dead, and these are the other ones. I rounded them so they weren't perfect, 17, 47, 79, and then 100s. All right, so here I've labeled the axes. We've got percent dead on the Y, and then the percent concentration and the milligrams per kilograms concentration. There's only 6 groups, so I just labeled 6 of the 7 things on the bottom here, and then you plot in. So the lowest concentration was these ones on the most left here, and they had 17% death, so that would be approximately around here. And then this one also had 17% death. Then the next group had 47% death, so that's up here. And then we had 79% death, so that would be 50, 60, 70, 79's up here. And then we have 100 and 100. So here's our graph. That's a nice little S-shaped curve, dose-response curve. Now figure out the LD50. So this is the 50% line right here. Come over here. Where does it cross? Again, it doesn't cross perfectly, so I'm going to pick the most quick location, which happens to be right here. We're going to drop it down. So we're going to say, and it happens to be on this like perfect line. So we're going to say it's 0.1% and 0.005. Also, let's figure out the threshold. So where do we start to see an increase? And it's after this point. So after this point, it starts to go up. So this is your threshold. So right here is your threshold amount. So I get that the LD50 was 0.1%, or that equates to 0.005 milligrams per kilogram dose. The threshold level was at the next lowest concentration, so that's the 0.01% or the 0.0005 milligrams per kilogram. Now take this information and apply it to humans. So how much would this potentially, if we had to estimate, because we can't test VX nerve gas on humans, so we're going to test it on rats or something and then apply the data to humans. So how much VX nerve gas might it take to kill humans if they weigh, the humans that we're analyzing are 90 kilograms. So we're going to take 90 kilograms. We're going to set up a unit conversion using our LD50 total. So it takes 0.005 milligrams of VX per 1 kilogram of rat, and we're going to assume that rats and humans have the same thing. That may be a crazy assumption, but that's what we're going to do. Cross these out. We hate decimals, so I'm going to shift forward 1, 2, 3. 1, 2, 3. So I'm basically taking 5 times 0.09, and that means that 0.09 times 5. If you don't like multiplying by fractions, pretend that the decimal's not there. So I have 9 times 5, which is 45. And then I have to add back 2, so I'm going to add back 2. So my answer is going to be 0.45 milligrams of VX would kill half of a group, which is not a lot. And that's why VX nerve gas is so widely used in chemical warfare. You made it!